Good evening, everyone. Today I'm going to talk about the retarded potentials. Previous class, I was discussing about oscillating dipole antenna. So, what is oscillating dipole antenna? If you look at this particular screen, I am sharing the whiteboard. If it is a positive and negative, separated by small distance. So, between these two polarities, if the length is very small, then it is called as oscillating dipole antenna. That is what we have seen in the previous class. Today's class, we are going to see about retarded potential. What is retarded potential and what is advanced potential? Then what is how to calculate the fields? That is what we are going to understand. So if you look at this particular slide, what you are seeing here is it is a retarded potential. This is retarded potential. So in order to understand this retarded potential, we need to know the basic Maxwell's equations. What are Maxwell's equations? These are the four Maxwell's equations. So del cross H equal to J plus dou D by dou T. If it is free space, J equal to 0. Del cross E equal to minus dou B by dou T. Del dot D equal to rho V. And del dot B equal to 0. So for static fields, the equations are different, and for time varying fields, for free space, the equations are different. There is one more relation called D equal to epsilon into E, B equal to mu into H, J equal to sigma into E. These are the relations between fields and flux densities. Coming back to retarded potentials, here when the wave is propagating, it is propagating in the forward direction. We assume that the wave propagates in Z direction. So we write e power minus gamma into Z. This gamma is called as propagation constant, which involves alpha and beta, where alpha is attenuation constant and beta is phase shift constant. As long as the waves remain to free space, the attenuation can be neglected. That is, attenuation value is 0. Now, coming to the derivation of this retarded potential, we have to know what is retarded potential and what is advanced potential. Again, I am going to show you. This is a current carrying conductor. The length is L. We are taking a small length dl, and this small current element IDL, the current flowing it is I. So at a point P, we are going to calculate the potential at a point P. When we are calculating the potential, which is at a distance of R, the cause and effect. Here we are transmitting current, that is the cause, and the effect is felt immediately. Can you say that? No, it has to travel some distance. So it will take some delay. The effect is felt after some delay time. So these type of potentials are called as retarded potentials. Now the question is, what is advanced potential? What is advanced potential? If the effect is felt instantaneously, or the cause should have started some time before. So that is called as advanced potential. This is the basic difference between advanced potential and retarded potential. Every student should understand. What is potential? It is the work done in moving a charge from infinity to a point in the field, or it is the work done against the field. I hope you can recollect about the potential which you have studied in electromagnetic field. So we are going to calculate the fields at point P. So what is the basic element for electric field? This is electric field and this is magnetic field. Charge is the basic element to calculate electric field. Similarly, current carrying element, ideal, is the basic element to calculate magnetic field. This is direct method. There is one more indirect method. We can calculate potential and electric field. Here we can calculate potential and magnetic field. So here I think you are understanding. This is charge Q. From charge we can calculate field directly. Similarly, from ideal we can calculate directly H. Another method is through potential. First from charge calculate V, then E. From ideal current carrying element calculate A, then H. So this is how we calculate the fields. First we need to understand how to calculate these two potentials. Coming back to my slide, that is retarded potential. So we are talking about Maxwell's equations, right? In Maxwell's equations, if you see, this is the solution for Maxwell's equation where V equal to, if it is a line charge density, line integral rho L dl by 4 pi epsilon naught into R. It is a volume charge density, surface charge density, surface integral S ds by 4 pi epsilon naught into R. It is a volume charge density, volume integral rho b dv by 4 pi epsilon naught into R. The relation between electric field and potential is E equal to minus del V. Del square V equal to minus rho by epsilon. It is a Poisson's equation. If rho, that is charge free region, then rho equal to 0, del square E V becomes 0. These are the equations for magnetic potential. Now let us consider B equal to del cross A. What is B? Magnetic flux density. Del cross A. A is magnetic vector potential. So from this we have calculated del square equal to minus mu j. Now retarded potential can also be calculated as, so here these retarded potentials can also be calculated from Maxwell's equations. So radiation is a time varying phenomena. So we need to consider time varying Maxwell's equation. Del cross E equal to del cross E equal to minus del V, substituting in place of E minus del V equal to 0. But from Maxwell's equations, del cross E equal to minus dou V by dou T. So these two are contradicting. So from these two, what we can conclude is these equations satisfies both static and time varying conditions. E equal to minus del V minus dou A by dou T. So next one is del dot E equal to del dot epsilon into E equal to epsilon into del dot E. Epsilon into del dot, substituting this value, equation 4, minus del V minus dou A by dou T. We get del square V plus dou by dou T of del dot E equal to minus rho by epsilon. This is one of the Helmholtz equation in terms of potential. So del square V equal to minus rho V by epsilon. This is for static conditions. Del square V equal to minus rho by epsilon minus rho by dou T of del dot A. This is for time varying conditions. Next, we consider the magnetic equation. Del cross H equal to J plus rho D by dou T. So del cross H means del cross B by mu. Del cross A by mu equal to del into del dot A minus del square A by mu. From this, we have the vector identity del cross A equal to del into del dot A minus del cross A. So the right hand side can be written as substituting this value in this equation J plus epsilon dou E by dou T. We know it's E equal to minus del V minus dou A by dou T. Substituting the value and calculating, we get del into del dot A equal to minus del square equal to mu J minus mu epsilon into dou U by dou T plus dou square A by dou T square. Here we need to make this term equal to 0. So we have to follow one condition, that is Lorentz gauge condition. What is Lorentz gauge condition? Del dot A equal to minus mu epsilon dou U by dou T. If it satisfies this condition, then this equation reduces to del square E equal to minus mu J and del square V equal to minus rho by epsilon. So these two equations are called as Helmholtz equations in terms of potentials. And the solutions are V equal to V naught e power j omega t and A equal to A naught e power j omega t. After solving these two equations, we get the solutions as V equal to integral V by 4 pi epsilon naught into R, A equal to integral mu I dV by 4 pi into R. So this is the diagram I have shown earlier. From this, we are going to replace, since V is a function of space and time. Similarly, A is a function of space and time. We can express V as V of R comma T. 1 by 4 pi integral rho of R dash comma T by R dash dV dash. Similarly, A of RT equal to mu by 4 pi volume integral J of R dash comma T by R dV dash. Here I told you that if it is a retarded potential, T dash equal to T minus R by V. If it is an advanced potential, T dash equal to T plus R by V. Since these two are retarded potentials, we are substituting T minus R by V in place of T dash. So these two are the equations for retarded potentials for V and A. I hope you understand this concept. And now I'm going to tell you about few questions. Note down the questions. The first question is, what is potential? Differentiate retarded potential and advanced potential. Second question, derive retarded potential from basic Maxwell's equations. Derive retarded potentials from basic Maxwell's equations. Third question is, what is Lorentz gauge condition and Helmholtz wave equations? These three are the assignment questions and important questions in this topic. I hope you enjoyed this lecture, and if you have any doubt, you can call me at any time. Thank you.